Uh-huh. The port is servicing the ship, and the ship is servicing the freight. Now, there are two main types of ports in the world. Those ports that take advantage of the quiet waters provided by nature, or those ports that need artificial sheltering. Now, because the sheltering structures are in contact with waves and currents, with the physical actions of the movable environment, which is the sea, the sheltering structure is a main part of the port engineering. Although the financing of ports and the money making of commercial ports is not in this necessary work, but is in the quays. But to have an efficient movement in quays, sheltering structures are needed. We are going to pay short attention in this first lecture of today to these sheltering structures. Sheltering structures may be provided by nature. This is an example of the Spanish port of Vigo, in which the nature, through the island seas, provides the necessary shelter to this very important Spanish port. The port of Vigo needs no sheltering works because nature has provided it. You can see here there's clouds, but with waves in the open sea energy is stopped by this natural formation, which are the CS islands that protect the bay of the port of Vigo. That permits this enormous port to develop its port activities within sheltered waters. Now, in the old times, ships made round trips of 1 year. So if there was a rough sea, there was no problem at all of not making port operations during rough water and just waiting for the water to come in. But when you measure the calls in ports of ships in terms of hours instead of minutes, you cannot stop port operation because of rough weather. So sheltering structures are needed. If those sheltering structures are provided by nature, it's much cheaper, the operation. But when nature does not provide that structure, they must be made by the man. This is a man-made structure that has the objective of sheltering water to permit the port operation and distinguish between water with a high content of energy, where the ports commercial operations are impossible, and quiet waters where commercial operations are possible. This is the objective of these cold breakwaters. There are two ways of keeping quiet water, or distinguishing quiet water from agitated or energized waters. The sheltering permits this type of operation. You cannot operate, you cannot pick up or leave a container on a ship if the ship is moving due to the energy in the water surface. To do this operation of transfer between the lorry and the ship, and between the ship and the lorry through the crane, the ship must be in a stable position. And to have the ship in a stable position, the water must be quiet. Now, you make money here. This is the area where the money is made. This is provided either by nature or by the government or by, we will discuss about that. But the money is not here. The money is here and the port operations are here. But to do this efficiently, this is needed. Now, we will come back to this point, but naturally, the money-making port activity is close to the sea, and the limit between the sea and land is the coastline, and the coastline can be a cliff over a beach. So both cliffs and beaches are an important part of the port, but once again, it's not where the money is made, but there is a conflict of interest between beaches and ports, and between energy arriving to the area to make her operations in an efficient way. So all of this has to be looked at as a system. Just this is the building in which we are here now in Madrid. This is the non-liberty statue in New York, in the port of New York. This is the La Tour Eiffel, at the time the largest structure, steel structure in the world. And this is a breakwater. Actually, this is the breakwater of Punta Lucero in Bilbao in Spain. You see the dimensions of this type of work. This is a building. This is this university. That is just to make us an idea of the dimensions of what we are talking. From the point of view of the civil constructor, the number of units to be built are very simple and few. Here, nucleo, concrete, blocks, filter, 1, 2, 3, 4, 5 units. That's all. But you may be working with that unit for months, even for years, because this actually is a mountain to be moved from on land to under the sea. You don't see it. That's just what you see. But this part that you don't see is there because without this part, you cannot have that part. And this has the objective of making port operations viable here to avoid the energy at the open sea to arrive in the operational port areas. Now, how do you work against the sea energy? Our objective is to stop the sea energy and to have still waters. How do you do that? There are mainly two ways, as always. You can either stand in front of the energy and destroy it, or reflect it. So there are two types of structures, the destroying structures and the reflecting structures. This is a destroying structure. You just put here a number of blocks, and these blocks, and there is a large discussion, many people think, and they are in an error, that it's the block dimensions that stop the wave energy. Actually, what we think here is that it is the air within this concrete or stones. The air is compressed by the water, and when the air is compressed by the water within these restricted areas, it comes to a moment where the pressure of the compressed air is enormous, and then the air explodes. There's an explosion, and that air explosion within these spaces produce the consumption of the wave energy. So the energy is dissipated in these continuous explosions in these areas, in these spaces within the blocks. Naturally, the most number of explosions and the most energy dissipation takes place in the area where there is most energy in the waves, and that is close to the sea surface, because the energy of the waves diminishes as you get in depth. Now, it would be very expensive to have a full, complete dike with blocks or with big stones. So to just to support these blocks that must be very big, and the size of these blocks in relation to the maximum energy they are receiving, you need something just to keep them in place. And this must be as cheap as possible. But if you have here cheap product from a mountain, it will go out through the spaces in the block. So to avoid this material to flow back to the sea, because the water comes in and comes out. So to avoid to be washed out this material, you have to install filter layers. But the filter layers have the only objective of preventing the wash of the material that is just a support to the structure. And this structure has an important area and a less important area. Now, if you don't want the energy to come here from time to time, you can either make that quite high or put some concrete structure there just to reduce that volume. There's no other objective there. These are, you can use here special pieces. Now, there's a large discussion about these pieces. These pieces, there's a large discussion around the world, and we have no experience with that. Look here. If you use a block, you can use a big stone, but you cannot get out from the quarries very big stones. So when the stones are really big, let's say over 3 to 6 tons, when you need blocks of more than 6 tons in weight, it's almost impossible to get them to produce artificial blocks. And artificial blocks are concrete blocks. Now, if you put a concrete block of, let's say 20 tons, for example, and you put it against, put it here, you put it against the wave energy, and for any reason, this block breaks. Well, normally, how it breaks, it's a corner of it that breaks. So if a block of 20 tons breaks, it can be transformed in a block of 19 tons, of 18.5 tons, in the limit. In the worst of the cases, it can break through the middle. So in the limit, a block of 20 tons is transformed in 2 blocks of 10 tons, in the limit. Now, if you have, for example, that type of pieces, those pieces like this, you have dolos, you have tetrapods, these pieces like this. If one of these pieces breaks, because they are working, they are taking advantage of the interaction between pieces. One of these pieces broken is not 2 half pieces, it's just nothing. Nothing. There are many places, many construction companies that say that you avoid, that you use less concrete with these pieces, and that is a miserable question, because when you use natural stones, you put at least 3 layers of stones. When you put blocks, you put at least 2 layers of stones. And when you put special pieces, you just put 1 layer of pieces, with the enormous problem, that a broken piece is nothing, not 2 half pieces, nothing. And there have been a large number of accidents due to not understanding this very, very simple concept. Now, this is a dike which is prepared to receive energy from both sides. It's a very interesting thing, and we'll come back to it. But it's not the same if you have a dike parallel to the energy, parallel to the coastline, or you have it perpendicular to the coastline. So the energy, the angle in which the energy arrives to the dike is very, very important, and many other things. This is another type of dike, and this dike, in the sheltered area, you profit of the structure to create a quay. So you can moor ships at this side of the quay in quiet water, in quiet water. So you use this part of the dike to fight against the energy, and you use this part of the dike to support this part of the structure, which is the main structure, to have quiet water, and then you take advantage of this part of the dike to use it as a quay. But they are in the same thing, but nothing to do. This side has nothing to do with that side, although they are both parts of the same system. Well, this is another case. And the when there is a tide, where there's a tide, the maximum of the energy concentrates around the sea level. But if there is tide, the energy, you never know when you have maximum wave, if it's in high tide, in medium tide, or in low tide. So the maximum energy when there is a tide runs from here to here. You never know where. So all of this part is accepted and attacked by the energy. Now, in depth, you receive less energy. So you don't need such big blocks in the depth. Very important to establish exactly which is the limit of the depth, because if you make a misunderstanding here and you lose these pieces, then the structure will fail. And there have been many, many cases. That's a very interesting work. We have been working a lot in this, and we will come back to this if there are questions. But Spain, unfortunately, Spain has very, very, very few natural ports. The main ports of the world are natural ports: Hamburg, Bremen, London, New York. They are like the port of Vigo. But in Spain, we have Vigo, the old part of Bilbao, not the new part. The old part of the port of Cartagena. The only port in the Mediterranean, the Spanish Mediterranean, is the port of Cartagena. Just one port. All the others need this type of structures. Now you fight against the energy either with air within the blocks or with water within the blocks. This is a completely new concept, but from the aesthetic point of view, when the dike is close to the city, with this type of structure, you create white water and you do not disturb the vision of the ship from the city. And most main ports are within the city areas. So it's quite important not to protect the water with high breakwater structures, but with wide structures. But you don't need material here, so it's much cheaper just to leave water within the space between the dikes. This is a new concept in which we have been working a lot and in which we really believe. And well, and I'll take something. Let me see. Let me see if I can find a very important idea, because history plays an essential role in what we are talking. At the beginning, quiero bajar esto, no sé cómo, no, quiero ver todas las líneas, quiero ver el vídeo vertical. Aquí, en grande, en grande. Vamos a ver. Ya lo. Así, gracias. No, well, there is another way. There is another way of. There is another way. La base de datos. ¿Dónde hay diques verticales aquí? Las diques verticales son las de cerrado. Así. there's another way of protecting the water, and that is with a vertical wall. And that vertical wall, there are two types of vertical walls. The ones done correctly, where they can be done correctly, and that is in most parts of the world, except in countries like Japan. And Japan is a master in this type of structures that look one thing and are another thing. I will come back to this point. Well, I will say, in the not Japanese engineering world, a vertical structure fights against the energy by reflecting the energy. But to be able to reflect the energy, you need enough depth so as to be able to reflect the energy. In Japan, this type of structures are made in shallow water, so the energy, the wave enters, attacks the structure broken. And if it is broken, it cannot be reflected. So that is a third type of structure. But let's come to history. In the old times, what would a Roman engineer do? Well, if you have the bottom of the sea, the surface of the sea, and you want to have here white water, the easiest thing is to build a wall, just a wall. But when there is a big storm, the wall breaks. And what is a wall broken? A wall broken is a number of blocks. How do you repair a number of blocks? Can you put a wall on top of these blocks? It's quite difficult. So the easiest thing is to put more blocks on top. So the two main structure types for the last 5 to 6,000 years, in the beginning they were vertical structures looking for reflecting energy, but once broken, they were transformed into dissipative structures with slopes to dissipate energy. But the dissipation structure is the result of a broken initial structure. This is a very important concept to understand things. Understand history is very, very important, because there can be big mistakes. For example, I'm going to show you a big mistake in space. This is a big mistake in the port of Malaga. Look, this is the port of Malaga. The historic breakwater of the port of Malaga was a slope. This was the old dike. Now the old dike interferes. First of all, it creates a sheltered waters of the port of Malaga and from non-sheltered water. But it interferes with the movements of sand, because the ports are making the coastline, and the coastline has sand movement. Now, that sand is stopped by the dike, and the sand stopped by the dike creates an artificial submerged beach. And that beach creates the wave to break before arriving to the coastline, because a good beach is a protective structure, the same as a dike. It's a protective structure. It's a long in distance. This is short in distance, but it has the same effect. Now, this was the place where ships waited to enter in the port of Malaga. But they made an enlargement of the port of Malaga with a vertical structure. But the vertical structure reflects, it's like a mirror, reflects energy. So in this area where the ship used to wait before entering to the port, now it's like hell, because the energy coming against the dike and reflecting, you see that here there's double energy because it's the energy coming and the energy leaving. So they have duplicated the energy content in this area. You must be careful because with dissipating structures, you dissipate energy. With reflection structures, you send energy to another place, far from where you have a protected area, but you still have the energy. You have doubled the energy content in that area. Very simple ideas, but very important, and a lot of misunderstanding in the port industry, even by specialists. It's astonishing how this thing works. So coming back to these main structures, I'll show you. This is a dike, the dike of Vieja, the part to fight against the energy, the sheltered water. Now, this structure produces no money at all. Well, it permits making money within the port area, but it's not a money making in itself, but it is needed. Well, we can see so many examples in different parts all over the world. Now, a very important detail is that in this area there is a different, the direction of the energy makes a big difference in the resistance of the dike. Now, in this part, all direction. So, being a world direction, for sure you will find the world direction in this area. So, this area is much more sensible than the rest of the dike. Because of this, well, in Spain we have the longest dike in the world, which is this one, dike of Juan Carlos I in the port of Huelva. This is the entrance to the port of Huelva. There is a lot of sun moving there from Guadiana River, and that sun stops here. So this was open sea, and the beach advances. So when the beach advances, the sun comes in. So they make longer dikes. Then the sun continues to advance, and by now this procedure has led, and also a big misunderstanding of the sun movements, has led to a dike of 21 kilometers, the longest dike in the world. Because of this, this dike could be removed from here, because now the function of dike has been substituted by the beach that the dike has created. But once the beach is created, you don't move the dike. So most probably you could have, even in the limit, have had a movable dike, advancing, creating beach, leaving the beach behind you, and advancing the dike. We also have the deepest dike in the world. How do you build that? Well, now you build the dike in the nucleus. After the nucleus, the filter areas, and then the protecting areas, and then the concrete level. But when building you cannot put the protecting area if you don't have a nucleus to support it. But if a storm comes, this front part of your work will disappear because it is not protected, and it cannot be protected because you can only protect it once you have built the nucleus of it. So this is a big problem of the port constructions. Actually, the port is built, these works are built like walking 2 or 10 or 20 meters to the front and 5 meters back. 5 meters, 1 meter back, 25 meters, and so on and so on. So there have been many times in the past time that if you were not able to build faster than the removal of material of nature, you could never finish your works in a port, because to finish a breakwater, you have to be careful that you are able to put the material at sea at a higher speed than that in which nature takes it out from you. So when you have bigger mediums to construct dikes, you can go faster, and naturally you should build during the summer where there's no energy, and during the winter you just protect your work and wait for the summer, because you normally you cannot work in winter because you will lose too much material. This is how, for example, a barge car opens, and you see how the dike is advancing, and that to advance, it is cheaper to work from land. But to work from land, you have to put the bottom of the sea up, and to put the bottom of the sea up, you have to use naval elements. If not, you cannot elevate the bottom artificially, the bottom of the sea. Now, this is what blocks have produced, and the number of blocks of the dike is a full industry, because most of the blocks you don't see them, they are under the water. And most of the blocks used. Now, this is a dike structure. You see how it has been advancing, and you are prepared for the winter. For the winter, you protect the whole of your work, and you get away and wait for next summer. And next summer you will have some problems here, but you have protected. Then you take out this part and you continue to advance. ¿Cómo? Sí. Corto fijo. You make part of the dike from the water, part of the dike from land, and the main part is the protected. Once it is protected, from here there's no problem. But this part from here, that is in a very dangerous situation, because a big storm will throw all this away. And it happens quite often. Now, once the blocks are in place and the concrete wall is built, all that part is safe. The problem is this part here. That's just to see the dimension. Enormous, a lot of material involved. From the economic point of view, when you make the cost-benefit analysis, there are some type of projects in which, for example, in one of these dikes, the price of concrete is not a fixed price, because the work itself affects the market price of the concrete in the country in which the work takes place, because it absorbs 100% of the concrete production in the area. The steel used here, you use 100% of the steel production in the area. So the work itself affects to the price in the area. Prices in this type of macro projects are not fixed prices, because the work itself interferes with the market price of the very few products that come in here, because here you just use concrete, stone, water, and steel and sand for products, but massive quantities of those four products, massive quantities. Now, the other way of fighting against the energy is with vertical structures that need a special protection, because when the energy is reflected, there is a strong water current going in this direction that will create problems, big problems in this area. The same as in most ports, when big ships come to moor against a quay, and if they put a propeller, the current of that propeller creates enormous problems in this part of the quays. And in many parts, ships are growing. Ships enter the quay just in their limit, and if they use their own propellers or the lateral propellers, after several port operations, they ruin the structure. And many people are not, they do not understand that they are ruining the structure because of normal port operations with big ships. Well, we have, this is now, here it's a vertical structure, but the question is, does the wave have space enough to reflect the energy, or there is a reduction that brings imported waves already broken, and a broken wave energy cannot be reflected because it is broken. So behind this concept, there are two completely different types of vertical dikes. Those that can reflect because there is enough depth, and those that cannot reflect energy. Well, these are cases, these dikes in Japan, the coast of Japan is, you have a volcano, and in the Canary Islands, and you have the sea here. You cannot put a slope, because if you try to build a slope here, you cannot build it. So to build a dike here, you have to come to a vertical wall. If the slope of the land is steep, it's completely different if it's close to a beach, and below the sea you have a beach like this. Then here you can choose between making this and taking off this land, or putting something here. It's completely different in those coastlines, in sedimentary coastlines, or in erosive coastlines. So it's not something which you can use. You can choose between using a reflective structure or a fixed structure. It's something that the configuration of the land forces you to come to one solution or to another solution. This is one of the deepest vertical dikes in the world, because this is just a base of the dike. The energy, the limit of the energy is around here. So all this part is not affected by wave energy. So this is just leveling or putting up the bottom of the sea. This is the dike structure, and this is a full dike structure. But look at the depth here. This is 15 meters of depth, because it's 3 meters plus 13 meters is more than 16 meters of depth. And this is 54 meters of depth. In submarines, for example, when the submarine goes deep, it's not affected by the wave. The wave energy is concentrated. So this looks like a Japanese dike, but it is not a Japanese dike. It is a real vertical reflecting dike in an enormous depth. If you don't look, this is 34 meters here, plus the tide. If you look at this without taking account of the depth, it looks like a Japanese dike, but has nothing to do with it. It only looks like it, but it works in a completely different way. Well, how do you build a thing? How do you build a thing? You build in a floating. You have a floating structure, and you begin to build concrete, and you make the concrete. You put a lot of iron and concrete, and then you build this station, and this station you move it, you push it by a ship or something, and it comes into position. Here, to build this station here, you need a concrete plant somebody working or 100, 200 persons working on iron, and you need this structure that while you are constructing the dike, it sinks so that you have the block. And the size of the block you can build does not depend on what you want. It depends on the machine you have, on the floating dike you have. And these are the blocks built there and wait to be moved like that and put into position to build the dike. They come up to the depth in which you can work over the water, because it is much more comfortable to work on top of the water than below the water. If there are things to do up from this depth, you make it from the dike itself once the dike is in position. Very important how the dike is positioned in the bottom of the sea. The bottom must be flat, because if it is not flat, your caisson will be not horizontal naturally. This is how you move it. You have necessarily hollows there so that it floats. When you move it, you have to put so that water does not come in. And once it's into position, you take out those things. First you put water, you sink it. If you have made some position, you can take the water out and reallocate it. And once it is located, you put sand or you put stones or whatever inside. You see? Here you put sand, first water, you sink it, then you put so or whatever, and then you continue to build your dike, but the people are not swimming, they are on land. This is a dike being constructed. The end part of the dike is the most sensible one, and in this position it's more resistant than this one, so that is why there's and it is cheaper to put two blocks of the same size. I'm going to go a little bit quickly, so you see how to build here. Very important, very important, and a lot of misunderstandings here. We distinguish between what are maritime works that can be what we have been seen, protective work or money-making work, and marine structure. The main difference here is that this one affects the wave energy and are affected by the wave energy. This one are affected by the wave energy but do not affect the wave energy. If you put a needle at sea, the needle is affected by the wave, but the needle does not affect the wave. And that makes an enormous difference. The offshore structures are maritime structures. The offshore structures are prepared to support platforms to put oil rigs or whatever. But the intention is not to fight against waves. It's a different concept. And there's so much misunderstanding of this point. Well, I'll come quickly to this part that we will leave. I was a joke a long time ago in Spain. There was a joke. This is the old way of looking at this problem. Now this is the old way in which we thought that the stability of the dike depended on the stability of the blocks or of the rocks of the dike. So this is the study of the forces that stabilize and destabilize the blocks. Now we think that the energy consumption is because of this air explosion within the block, but that's another question. Now, what forces are acting there? Forces against the rocks, forces like this flying like an airplane, and okay. Then you work with all these forces, and you come to a nice expression, in which you have things depending on the fall, on the density, on the roughness, and so on. And then you put all of them within one parameter, which is parameter K. I'll come back. You separate that things that are easy, and all those things that are not easy. And the first was 1934, 38, 50, 59, 65, 80, 2012. It's always the same. And this comes to expression of a coefficient that can be determined easily, the slope, which is easy, density of the water, density of the material, and K. And K is all the rest. And all the rest is about more than 1,000 parameters. So this is 1,000 parameters and 1, 2, 3, and 4. 4 parameters, 1,000 parameters, and the wave height. This is the main point, because the wave height is the third al cubo, la tercera potencia. And it's not exponential thing. Or this audio. And you have to you have to see how a dike can break, and you must be sure that it not it can break because the soil, the bottom of the sea, has not enough stiffness to support the weight of the dike. There are many reasons, not just losing the pieces up there, not just those. There are many others. Or that's a very interesting discussion here. And Japanese technicians, or European technicians that do not read carefully Japanese papers make this enormous mistake. I will. If you have this quantity of water, the pressure here, if we measure pressure, here you have this pressure in this same quantity of energy. Here you have more pressure, here you have more pressure, and here you have enormous pressure. That is like if a bee stings you. If a bee stings you, harmful. But it is completely different. Completely different. Having a very high pressure in one point, that having all the walls being stuck by this pressure. One thing, you may have enormous punctual pressure, but there are dikes that are calculated, taking into account this high peaks of pressure, but not considering that this is a pressure at what point. They extend that pressure to the whole of the parameter, and they come to enormous structures with enormous costs that make not viable the commercial operation behind those walls. That is where the money has to be made. That's a very important thing to take into consideration. And very quickly, I went through this presentation And just to go very quickly and to put it in the learning management system, before we stop here, I would like to say two things. First of all, that the port industry is at the service of the ship, and the ship is at the service of the goods. So what is really important is the goods, but the goods are money, and when there is money, there are people that want to take that money from others. So the goods, the money in the goods need military protection. So always from history, naval ports and commercial ports have gone together. Now, the ship, the commercial ship that needs a protection ship close to it needs capacity and to move. And it can move either by the wind, by the oars, or by other things. And it has a material. And it's a traditional this construction of the old port structure are one of the techniques because the cycle is where you maximize the capacity and it's very expensive to have quiet water because of the breakwater. So there are some places where ships have to get through, and through those places that detect the size of the ship. And it is the size of the ship that determines the size of the port. Do not make the port of the whatever size you want. It's determined by the places by which ships have to get through. And there these are the ship lanes. This is real data. And out of this real data, you see, well, these are points of the world where there is a lot of sea traffic. Look, on the other part, when there is less traffic. Why? There are many reasons. But, well, where is traffic? Rich, there's a lot of traffic or areas in which there are a lot of natural resources. Natural resources create traffic. Now, the ships are adapted to the type of goods to move. So, and they are completely different size, different. One ship is equivalent, one 18,000 TEUs is equivalent to 30,000 lorries or something. No? If you have to get through the Panama Canal, the size of the Suez Canal or the size of the Panama Canal determines the maximum size to which you can build your port system. The port, this is the port of Rotterdam, 46 kilometers of port. It's a perfect interaction. The name of port is a very old concept. It's different port installations within a port area. This is the delta of the Rhine River, although they changed the name Port of Shanghai. So when you look at the port, what's important is the quays and the land operation and the sea operation and the transfer between land and sea. But to make this possible, you have to have enough depth, clean water, and still water. But the money is here. But that is needed. That is the message. That is the message. It is needed. Those are the port of Singapore. When you talk about the port of Singapore, you are talking of this land area and this connection to the ship. But an efficient connection to sea needs efficient connection to the land transport system. That means inland waterways, railways, and tracks. and you need efficient operations at the doors. You need to minimize the movement of the boxes within the storage area, and that is the important part from the commercial point of view. We are talking, and we have been talking this week a bit about green ports and about LNG, liquefied natural gas, as a fuel, and naturally the places where ships need fuel are in close relation to the ship lane. So Singapore, Rotterdam, and various countries, Belgium and Holland are the same port system. Gibraltar, Algeciras, Melilla, Málaga is the same Gibraltar area. Fujairah, Busan, Hong Kong, New York, Long Beach. This area needs, because there's traffic, it's growing traffic, and something is needed here and something is needed in Brazil. There's no doubt about that. So it's in the future. Okay, so I went completely rápidamente y lastly, ¿dónde está las cosas? I am going to go very quickly through this presentation because just to say that the ports have to be the coast, and to understand a port concept, you need to understand how the coastline works, because you need to have the ports in the coast, and the port is a commercial system in quite a tight relation with the people of the city. So a port needs to be in contact and has a dialogue with the city area, but it also has a dialogue with nature. So our program, Smart Cities Need Intelligent Ports, which is developed by our Italian colleagues, try to put on top of the table the knowledge, the social knowledge related with the complex relations between the social structure and the port activity. And there's another important part, which is the relation between the port and the coastal line. ¿Por qué no anda? Algo hecho mal. ¿Por qué no anda? ¿Dónde tengo que pensar? Gracias. I will go very quickly because there are two types of coastlines and they are different, and you have to look at them in a different way. Well, first of all, we must remember, particularly now we have the new lock coast in the Spanish coast, and so many stupid concepts on top of today. But one of the most stupid concepts you can even hear, and you can hear everywhere, is the relation between the climate change, the level of the sea, and its relation with the coastline. And a simple look at this map of the world, you see that this part of the world, they were mixed together, and it's a fracture, and this is separating. We have measured it with the ocean drilling program. We measured, and the speed of separation is 1.5 centimeters per year. It has been measured, but these movements do not take place in an horizontal plane. They go up and down. So what it is relevant in a coastline is the relative position water-sea, and that has nothing to do with the sea level. Absolutely nothing. It's a big mistake. A big mistake. Now, it's a very important concept also. That is that most of the surface of our planet, of the Earth, either two-thirds are covered by sea, and an important part of the other third has origin in marine sediment. Now, the coastline, we study the coastline between deltas and estuaries. That is, between places where rivers and the sea come together. And when a river and a sea come together, it can come in the way of a delta, and a delta, as you have heard that in other classes, this was the original line, coastline, and the river has brought this land, and because the river is more important than the sea, the river and the land of the river advances from the sea, and that's creating a delta. Or when the other way around, this the Nile River. The Nile River is an important Nile River. You see here the ancient coastline, and the river, the water carries water and soil, and that soil carried by the water of the Nile River creates the Nile Delta. Couple of thousands of years ago, this was sea, and because this is a small sea and this is an important river, the river advances on the sea. An important river, a small sea. If the sea is important and the river is small, this is the Ebro in Spain. You see here the old coastline. Here the coastline, you can see, and this is the old coastline. Now Hamburg. Hamburg, this is the river is not able to create a delta, and it's an estuary. And the port of Hamburg takes advantage of that situation. Moreover, because it's very close to the Baltic Sea, you have this canal, this canal here going from the Baltic Sea to the North Sea and the entrance of the port of Hamburg. This is the canal of Kiel, the Kiel Canal, which prevents the ships going close to the Swedish and Danish coast. This is the Tajo River and the port of Lisbon. The Tajo is an important river, but it's against the whole Atlantic. So the Atlantic creates a big estuary, and the city of Lisbon profits of that to create the port of Lisbon. Now, the coastline, this relation between the coastline and the sea leads either to coastlines in which sand moved by rivers is deposited in the coastline, or coastline which is eroded by the action of the sea. And you cannot look at the coastline in the same way if it is an erosion coastline or if it is a sedimentary coastline. There are two completely different approaches to the problem. Well, I will not come through it, but just to remember, you have to remember that there are two ways. The sand moves in the coastline, and because of that movement, if you interrupt that movement, you have an area in a sedimentary. This takes place in sedimentary coastlines, not in erosive coastlines. You have areas where the coastline advances, and because of this human work, the coastline has been altered. It changes dramatically. That can be good, but that's another question. The first question is to know that it changes, to understand how it changes, and then the next question is to see if that is good or bad, or you want to change it in one way or in another way or whatever. When this port was made, the coastline was here. Now the sand stopped here, advanced, it continued advancing, and it came into the port. And then the port was shallow because of the sand, so they had to make this dike. But with this dike, the sand continues to progress, and they will have to make another dike and another dike and another dike because the sand is collapsing. Now, this part of the dike, you can remove it because it's useless now. This sand is substituting the function that had in the past time this dike, so you can just take this dike and put it there. Well, if you understand how this thing works, you can modify the coastline in any way you want to modify it. Once you can, using structures that modify the content of energy in the wave, and knowing that the energy is moving the sun, you can make nature put the sun in the way you want by play with the energy arriving to the coastline, which depends on the type, size of the sun you are using here, of the weather conditions, the direction of the wave energy, and what you install here that you can sit or below the water, it doesn't matter. Eh? But playing artificially, you can play with the energy to move the sand in the way you want to move it. The way you want to move it. That's very, very important. Now, for example, this is the Gibraltar area, and we must, you see here clearly, for example, that river has its way under the water. In the old times, this was the river, and you can see the Gibraltar rock is on top of a mountain, and the mountain you see from the sea surface, it's also below the sea surface. So we are used to look at the sea as a two-dimensional surface, but it is not a two-dimensional surface. The land has land and air, and the sea has land and water. And the difference is that the density of water is 1,000 times higher than density of air. But you must look at the problem in that way, which is completely different on how do seafarers and sailors look at the sea. For a sailor, even for a submarine captain, the sea is a two-dimensional world. For an engineer, a sea is like the land, but with water instead of air. It's a different concept. So we must look at the bottom of the sea, and if we don't have a good idea of how the bottom of the sea is, we cannot make efficient and intelligent port work. We cannot do that. You can do things adequately or not adequately. In my opinion, these are not adequate works, but works, not adequate work. If you want, to keep water flowing, you have to stop the sand of the beach. I mean, yes, this was a peninsula in the former time. Now it's no more a peninsula. This is the limit. The limit between Spain and France. Always road was on. This is something our in the lawyers in the Spanish Ministry of Asuntos Exteriores. I wrote a book with the former director of the jefe de la asesoría jurídica de Asuntos Exteriores, José Manuel Lacleta. Y I will speak that in Spanish. En Asuntos Exteriores están locos y siguen locos porque creen que la delimitación de la frontera entre España y Portugal en el sur, en Andalucía, en Guadiana, que está escrita en 7 grados 26 minutos 30 segundos oeste, está equivocada. Y están locos y hay comisiones de estudio y revisan los papeles, porque claro, esa línea ahora mismo está en mitad del territorio portugués, porque el Guadiana está aquí. Y lo que no son capaces de entender es que cuando existe esta delimitación, que fue hace, bueno, ya estamos en el siglo XXI, hace 2 siglos, los finales del XIX, el río Guadiana estaba aquí. Mira los meandros del río. El río estaba aquí. Hicieron la delimitación bien hecha, pero la dinámica litoral ha movido el río. Y entonces, claro, ahora los portugueses dicen que la frontera con Portugal está en mitad del río. Y en asuntos exteriores dicen, pero si esto es España, y ¿cómo va a ser España? Si esto es Villarreal de San Antonio, esto es Portugal. Entonces, según el tratado, esto es Portugal. Están locos. Porque no han sido capaces de comprender que las desembocaduras de los ríos se mueven, pero no se mueven a escala geológica, se mueven a escala humana, se mueven a escala de tratados. O sea, los 7 grados 26 minutos 30 están hechos sobre la base de que la costa es un territorio estable. Y fijaros si el concepto es simple. Todo el mundo entiende, esto lo digo en clase en todas partes. Si tú tiras un corcho aquí y te vas y vienes mañana, lo lógico es que el corcho no esté ahí, porque el mar se mueve. Si tú pones una botella vacía aquí, nadie se la bebe ni se la lleve, mañana está ahí, porque la Tierra es estable. Bueno, el límite entre una cosa tan dinámica como el mar y algo tan estable como la Tierra es razonable que goce de propiedades no tan dinámicas como el mar, pero que no sea tan estable como la Tierra. Se mueve, claro que se mueve. Vamos, se mueve y mucho. Y las leyes, la ley de costas que está en el Parlamento, ayer los de Greenpeace se encaramaron, tal, el legislador está acostumbrado a razonar sobre cosas, sobre tierra, y no es capaz de razonar sobre ámbitos que son dinámicos. José Manuel Atleta, hemos hecho un trabajo sobre la delimitación de los espacios marinos, porque el Atleta, cuando es embajador de España, cuando acabó la carrera, no, la oposición de embajador, le destinaron a la primera conferencia de Derecho del Mar. Y duró 7 años. Como había estado en la primera, le destinaron en la segunda. Y luego fue a la tercera ya como jefe de delegación y firmó en nombre de España los acuerdos de Montego Bay. Pero es una persona que ha estado en las 3 conferencias de Derecho del Mar. Y bueno, tenemos un libro muy bonito. Yo creo que es muy bonito porque le hemos dado la visión del ingeniero y la del jurídico. Esto la Cletra lo entiende, pero me costó muchísimo porque, y sus colegas de ahora, de Asuntos Exteriores, no entienden. José Manuel está convencido, ¿no?, que los ríos se mueven, pero hay muchos embajadores de España que, cuando dicen, como soy gente educada, te dan la razón, pero no se creen que los ríos se muevan. Claro, pues, pues, nosotros hemos llegado, pero esto también es solo para hablar un lenguaje esotérico, formulamos las formas costeras para que nadie nos entienda. Entonces, todas las siglas son mágicas, dinámicas o geométricas en positivo o negativo, y en función de la naturaleza, la condición de estabilidad, el tipo de perfil que es estable, hiperestable, estable, homogéneo, heterogéneo, científico por completo. Entonces, formulamos las playas. Pero como evoluciona el tiempo, pues decimos, de tal año a tal año tuvo esta formulación, de tal año a tal año, tal este, tal año, tal este, y con eso creamos una matriz, que es la matriz de evolución de la forma costera. Y esto lo presentamos en distintos sitios y entonces ya nadie se entera de nada y parece que no existe. Porque claro, es una forma de presentar, por ejemplo, esta es la constelación. Y ya pones esto, de esto es una playa, ¿no? Es una tontería. Los superíndices, que si el material es homogéneo o no homogéneo, y son los periodos de tiempo, pero queda expuesto así, queda, queda muy universitario. Y el concepto es que the shoreline is diverse, that's very important, and de sedimentación, y esto es erosionaria, and completely different sedimentary areas and erosion areas, completely different, and delta areas and estuary areas different. This is the same hotel. This is Torremolinos, and look, with beach, without beach. This is an artificial beach nourishment. But in the old times there was a natural beach. Because of different reasons, beach disappear. It can be created again. You can play with the coastline and nature. And there is a very important concept, and that is that in dynamic environments, doing nothing, which is the Rio Declaration, it's a big mistake, because doing nothing is not true that is doing nothing, is doing something. Doing nothing is doing something. En los medios dinámicos, no actuar es una forma de actuar. Es mentira que no actuar sea no hacer nada. En un medio dinámico, el no hacer nada es hacer. Es hacer. Para no hacer nada, hay que hacer. Y esto, en medio ambiente, hay muchas personas que están entender. This is a clear example. This was the old coastline in Spain. We talk about marina, when the port is excavated on land, and port when it is you gain water from the sea by using breakwaters. But in this area, there is a large anthropic pressure. So you must look at this. You can't look at this area only from the physical, from the beach dynamics, or from the wave dynamics. You have to look at it in another way. Look at this. You may agree or you may not agree with this way of occupying the coastline. I personally don't agree. This is Benidorm. Okay. But it is there. And you cannot operate and you cannot manage the coastline as if this phenomena was not there, because it is there. It could have not been there, but it is. This is a very interesting. This is different from the legal terminology. What is la plataforma continental y el talud continental, from the legal point of view, is one thing, and in the books of geology is another thing. So it's a big misunderstanding between lawyers and geologists. Now, it's very important to Europe, the integrated coastal zone management, because the port policy and the transport policy needs to take into account the integrated coastal zone management, and you can only look at the coast in an integrated way. You cannot look at the coast. You cannot look at the coast as an isolated thing from the rest of the world. So Spain and Portugal, which from the historic point of view, Spain, there are three different parts of Spain. This is Aragon, which is Catalonia, Valencia, Balearic Islands, and Aragon has been always in charge of the Mediterranean area. They have a Mediterranean way of eating. The ships are in the Mediterranean way, and all the ship and port industry is in the Mediterranean concept. There is Portugal, and Portugal has been navigating mainly with Africa and has arrived to the commercial areas in Asia, in the east, through the eastern way. And to navigate the Atlantic, you have to touch Brazil, because if you don't touch Brazil, you cannot go to Cabo de Buena Esperanza in Africa. You have to navigate that way and then come this way, because the Africa coast current permits you to come from Cabo de Buena Esperanza upward, but you cannot navigate it downward. So to go to the east, you have to go to Brazil and then come back. And that has been Portugal. And Castilla, which includes Galicia and Andalusia, has been in charge of the new world. Because we work with the old world, with the new world, which is North, Central, and South America, and with the third world, which is Asia. And this is America, navigating connections to America. That is Castilla with Galicia and Andalusia. Portugal is connections to the east and Africa, and Aragon and Catalonia and Baleares and Valencia are connections to the, but in any case, Spain is a peninsula, and the peninsula is almost an island. In an island, the sea is essential because a large number of products arrive by sea. So for an island and the smallest, and compared to Europe, Spain is a small island. And if we take into account that this is a mountain, the Pyrenees, and we only have a connection on land with France, here and here, with such a congestion that we are not communicated in an efficient way to Europe by land, because we should be connected by sea because we are almost an island. In Spain, they used to say why there is no traffic in the railway. Well, because traditionally, goods going from Malaga to Barcelona, they don't go by rail, they go by cabotaje, by shipping. Because the economic activity in Spain is in the coastline and in Madrid. So we have the Madrid-Valencia connection, Zaragoza-Barcelona, Zaragoza-Bilbao, Madrid-Zaragoza, this triangle here, and all the rest of the activities in the coastline. So the transport system is in that way. Okay, and with this presentation, we close our presentations for today. Thank you very much. I don't know if still there is some university connected and following us, and if there is any question for any of the universities that are connected. No, you know? Okay. Thank you very much for your attention.